All right, 3.2 is Rolle's theorem and the mean value theorem. They are actually very similar. The mean value theorem is a more general case of Rolle's theorem. So we're starting with something that's simpler, Rolle's theorem, and then we're going to broaden it to the mean value theorem and take a look at how things change. So to start with, Rolle's theorem says, suppose that f is continuous on the closed interval AB and differentiable on the open interval AB, and the end points match. F of A is equal to F of B. Then there is a number C in between A and B such that F prime of C is equal to 0. And you'll notice there's some space on the paper if you've printed out the notes, and I'm going to draw you a picture of what this is saying. We have an interval from A to B. We are saying that the endpoints match wherever they are. I don't care if they're high, low, positive, negative, but they match. F of A equals F of B. And I have to get from point A to point B continuously. So I can't have any jumps, can't have any holes, nothing like that can happen. Okay, I got to get there without lifting my pencil, so to speak. So no matter how I do that, whether I do something like this, or whether I do something like this, or whether I do something like this, every single way in which I can draw it, because it has to be continuous, is going to have some place where the derivative is 0. Now, the last graph that I drew has lots of places, so there may be more than one, but I'm only guaranteed one. This one would be an example of one place where the derivative is 0. Now, you also could have what did I want to draw? Oh, this one right here is what I want to draw. Like a straight line, kind of like what you were asking before, Alyssa. And on this one, the entire interval has a derivative of 0, right? So infinitely many points where the derivative is 0. It's not a very exciting graph. We don't see that kind of a picture very often, but it technically holds true for the definition. Our pictures are going to be far more common to look something like this. And you'll notice that the reason that they can't do this now, because we could have done that in the last section. We didn't have an example of one besides just my images I drew. But the reason this can't happen on this one is because it says it has to be differentiable. And that cusp, that sharp turn, is a point where it's not differentiable. So there's no cusps when we're talking about Rolle's theorem. So we're looking at places where I have this sort of an image basically happening. Okay, does that make sense? That there's no other way to draw that for that to work. All right, so we're going to do some examples with Rolle's theorem. There are some very important parts of these directions that you have to be aware. It says to determine whether Rolle's theorem can be applied. I'm pretty sure it was last semester where I did an example of one on a test, and Rolle's theorem couldn't be applied, which means that everyone who continued on to find the derivatives and set equal to 0 forgot the first half of the directions. You want to make sure that you actually can apply Rolle's theorem. So what are the conditions in Rolle's theorem? Well, f has to be continuous on the interval, differentiable on the interval, and the endpoints have to match. Those are my 3 conditions, and I have to test them, and you're going to have to show me that you tested them. Like, write them down. Do you guys remember doing the intermediate value theorem back on exam number 1, where you had some conditions and you had to show me that you checked the conditions? It's the same thing. So we're going to check the conditions first. So the first condition, is it continuous? So is this function, negative x squared plus 3x, is it continuous? Yes. And we want to talk, sort of just justify really quickly why. It's really simple to do so. It's continuous because it's a polynomial. Polynomials are, by definition, continuous. Our theorem. It's actually in your book that it's stated that way, back in chapter 1. So we get that sort of for free. Second one, differentiable. You get it for free too. It is differentiable because it's a polynomial. So it's not that it's hard to check the conditions, you just have to remember to do it. And then the third thing is that you have to check that the endpoints match. So I need to test that f of 0 and f of 3 actually have the same output. In other words, negative 0 squared plus 3 times 0 has to equal negative 3 squared plus 3 times 3. So what do I get if I plug in 0? I get 0. What do I get if I plug in 3? I happen to get 0. I don't really care that they're 0. What I do care about is that they match, right? These are equal. So I have now verified that the conditions all work. Once I have verified the conditions actually work, then it says, if I can be applied, then find it. Find where the derivative is equal to 0. So we're going to come over here now, and we're going to find the derivative and set it equal to 0. Okay, so what's the derivative of negative x squared plus 3x? Fabulous. Negative 2x plus 3. And we're going to set it equal to 0. So I have negative 2x is equal to negative 3. And x is 3 halves. I had 3 halves show up in my earlier lesson too, right? In 3.1. But do you notice 3 halves this time? It's on my interval, isn't it? Last time it wasn't. Here it is. And Rolle's theorem guaranteed that whatever I found, at least one of the values I find, if there's more than one, is going to be on my interval. So, sure enough, 3 halves is in between 0 and 3. So my C value, the one that I was looking for, is in fact the 3 halves. Is that good? All right, let's try another one. Same directions. We have to verify that it actually satisfies our conditions. So our conditions, again, are that it's continuous, differentiable, and in this case, f of negative 8 and f of 8 give me the same output. Those are my 3 conditions to start with. So the first thing is it continuous? Well, this one's not a polynomial. Okay, the fact that it has a power that's not a whole number means it's not a polynomial. So I can't just say yes it is or no it's not depending on that. I don't actually have that as a fallback on because I don't have a polynomial. It might actually be a good idea to graph it in your calculator and see, is it actually going to be continuous? So grab your calculator. Take a look at this equation in y equals, and you need to go on the interval from negative 8 to 8. So you can use the power key with a 2/3 power, then -1, and then you can set your window from negative 8 to 8. For those of you who maybe don't have your calculator with you today, let me sketch for you what mine shows. Mine looks something like this. Okay, does yours look like that too, for those of you who are able to graph it? Wonderful. Visually speaking, this is just a visual description we're talking about here, but does it appear to be continuous? Continuous. Yeah, it looks continuous from my graph. So this one appears to be continuous, and you can actually just justify by talking about your graph. But does it appear to be everywhere differentiable? No. So it fails right here. And a description is that it seems that there's a sharp turn or a cusp, whatever language you'd like to use, and it's happening at x equals 0. And to be honest, that's enough for this to all fall apart. I can't use Rolle's theorem. There's no guarantee that anything from Rolle's theorem will now work because it failed one of the conditions. Now, if you weren't doing this in order, or if you got confused, or if you kept going, I'm going to show you that the actual next part works, just because I want you to have practice in checking the third part of it, but there's really no reason to check part 3 of this. Do you understand that? So just for kicks and giggles, we're going to check it, but there's really no reason. So this is negative 8. It's x to the 2/3. So this is the cube root of negative 8 squared, and then minus 1, and then the cube root of positive 8 squared minus 1. All right, so let's do the positive one. What is the cube root of 8? Cube root's easier than the square part first. What's the cube root of 8? 2. What's 2 squared? 4. And 4 minus 1 is 3. You can let your calculator do it if you want to, but this one's nice enough to do on our own. What is the cube root of negative 8? Negative 2. But what's negative 2 squared? 4. And then 4 minus 1 would be 3. So this actually checks out. Oftentimes if one part fails, more than one part will, but this one, it isn't the case. But Rolle's theorem does not apply. Okay, it's not everywhere differentiable, or it's not a differentiable on my interval, or whatever phrasing you want to use. It fails the differentiability test part of it, so I don't have to check anything else. It simply won't work. All right, let's test one more. Same directions with Rolle's theorem. Okay, this is the graph of a sine. Again, sinusoidal graph. You've got this wave pattern going on, right? So it looks like this. We have to test our three things: continuous, differentiable, and that f of 0 and f of 2 pi are equal. So is it continuous? Yes, and again, we almost get it for free. It's because it's sine. Is it differentiable? Yes. Again, it's smooth, so it's because it's sine. And again, there's a theorem that actually proves that in your book. So it's not like I'm just saying it without justification. I mean, I am, but it is proven in your book that there's continuous and differentiable for sine curves and cosine curves. And we test the endpoints. So what is the sine of 0? It's 0. And what is the cosine of 0? I don't know why I said that. Maybe because I'm just moving too fast. Sine of 2 pi is what I want. Oh my goodness. What is the sine of 2 pi? It's 0. And of course these are equal, right? So all of this combined together means that Rolle's theorem applies. So Rolle's theorem says that I can take the derivative and set it equal to 0. So what is the derivative of sine x? Cosine of x. And I need to know where is cosine of x equal to 0. What do you think? Do you know, Sarah? What are you thinking? Uh-huh, that's one of them. There's another one as well. Does anybody know the other one? 3 pi over 2, thank you. Yeah, there happen to be 2, and these are both on my interval 0 to 2 pi, right? Like there's lots more places that this would work, but on the interval from 0 to 2 pi, these are the 2 options. So it's actually true that both are on the interval 0 to pi. So C is equal, in this case, to pi over 2 and 3 pi over 2. We're not guaranteed 2 values, but we actually ended up with 2 values in this one. Okay, so here's what I think I'd like to do. We have, obviously, the other half of this lesson, which has 2 examples and the definition and so forth. It's talking about the mean value theorem, and I mentioned early on that Rolle's theorem is a special case, and the mean value theorem just broadens things. So what I'd like to do is I'd like to adjust the homework so that the homework for this section is not due until it'll be after spring break, okay? But your quiz is still going to happen on Thursday. It'll just only go through Raleigh's theorem. So I would strongly advise you to do the homework for anything that applies to Raleigh's theorem for section 3.2, and then also to do 3.1. Okay, so 3.1 and 3.2 Raleigh's theorem questions. 3.1 will still be due Thursday because we have finished it. So yes, thank you for clarifying, Hayden. So 3.1 due Thursday. 3.2 will not be due officially until after the break's over, but the quiz on Thursday will include 3.2's Raleigh theorem type questions. Clear? All right. Have a wonderful couple days, and I'll see you all on Thursday.